Hello, welcome to today's Roots of Polynomials video, where in some ways we're working backwards from what we did before. Instead of finding information about the roots from the equation, we're going to be finding out information about the equation from information about the roots. So, to be able to do this, a quick reminder of what we looked at last time, which is that if you're given an equation, or a quadratic more specifically, of the form ax squared plus bx plus c equals 0, and you're also given the fact that it's got the roots alpha and beta, we can quickly find expressions for the sum of the roots and the product of the roots by using the coefficients of the quadratic. But now we're going to be reverse engineering that idea. Hopefully you're aware, of course, that if we've got a quadratic, you could factorize it, and the numbers you see in those factors then relate to the solutions or roots to that equation, if that equation is a quadratic with a coefficient of 1 in front of the x squared only. If not, then it makes the factors a bit more complicated rather than just looking at the number, the single number that's inside the brackets. But therefore we can use this idea in reverse. If you know the roots and you know your quadratic is one that's got a coefficient of 1 in front of the x squared, then you know what the factors are going to be, and therefore you can multiply out those brackets to get the original quadratic. But we do have to be careful because we are only finding an example of a quadratic with those roots that has a coefficient of 1 in front of x squared. But in reality, there are lots of different quadratics that all have those roots, and so it depends on what we're trying to find. For instance, all of these quadratics all have the roots 2 and 3, so it depends on what we're looking for as to which one we pick. And therefore we do have to be careful about employing this trick of using the roots to guess what the original equation was, particularly if we're trying to use that idea to lazily factorize. For instance, if you're given this quadratic, you could use the quadratic formula to find these roots, and therefore some students make the mistake of thinking they can just take a quadratic and factorize it using those roots directly. So for instance, in this case, writing this quadratic as this, but if you were to multiply out these brackets, you would very quickly find that these two things are not the same as each other. That's because ultimately, although we have found a quadratic using those brackets that has the roots x equals a half and x equals 3, it's not the quadratic we were being asked to factorize, because as we pointed out, there's multiple quadratics that all share the same roots as each other. But with that warning aside, because this is the Roots of Polynomials chapter, we're basically going to be trying to do this process of using the roots to find the equation, but in a bit more of an algebraic way, because we're going to be doing things in terms of alpha and beta, which are the unknown roots of an equation. Ultimately, if you know that your roots are alpha and beta, then in theory you might be able to write it in brackets as x minus alpha, x minus beta. If you were to multiply out these brackets, you would get this quadratic equation that looks like this. However, as different Roots of Polynomials questions use the letters alpha and beta in different ways at different stages of the question, a more general way of looking at this would be to say that the quadratic is of the form x squared minus the sum of the roots, lots of x, whatever those roots are, plus the product of those same roots, and then setting that equal to 0. That is, of course, only finding the equation of the quadratic, where the coefficient of x squared is 1, but then ultimately all the other quadratics are just going to be some multiple of this equation. So therefore they could also be found as well if need be. So let's take a look at an example. In this first example, we're given the quadratic 6x squared plus 8x minus 5 equals 0, which has the roots alpha and beta. Interestingly, we don't need to find those roots, because instead what we need to do is find a new quadratic equation with the roots 2 alpha minus 3 and 2 beta minus 3. All we need to do to find this new quadratic equation is ultimately find what the sum of those new roots are going to be, as well as the product of those new roots, because then we'll be able to use that structure we looked at just before to be able to find what this new equation is. So therefore, let's work that out. So our new roots are 2 alpha minus 3 and 2 beta minus 3. So if you find the sum of those roots, well, the good news is we can rewrite that and simplify that in terms of expressions to do with alpha and beta. We could, for instance, rewrite this expression as 2 lots of alpha plus beta, factorize the 2 out of the 2 terms with alpha and beta in, and then the minus 3 and minus 3 combine to make a minus 6. So all we need to do in order to be able to find the value of the sum of our roots is find out what the value of alpha plus beta is, which is something we have found out in the previous video, is something we can do without ever individually finding what alpha and beta themselves are. Alpha plus beta, as a reminder, is just going to be related to minus b coefficient of the original quadratic divided by the a coefficient. So in this case, that's going to be minus 4/3. So therefore, the sum of our two new roots is going to be two lots of minus 4/3 minus 6, which would be minus 26/3. So there we go, we've got the sum of the roots, but in order to find the new quadratic equation we're trying to find, we also need to know the product of these new roots. So let's do that as well. So 2 alpha minus 3 times by 2 beta minus 3. And so multiplying out those brackets, we'll get a 4 alpha beta, we'll get minus 6 alpha minus 6 beta, and then a plus 9. Of course, we realize although this looks initially a bit complicated, we also realize it's secretly just expressions involving the sum of the original roots and the product of the original roots, because it's just 4 lots of alpha beta, the product of the original roots, minus 6 lots of alpha plus beta, plus that 9 on the end. And alpha beta, the product of the original roots, can also be found from the original quadratic, because it's just going to be c over a, so that's minus 5/6 in this case. So therefore, the expression or value we want to find is 4 lots of minus 5/6, minus 6 lots of minus 4/3, plus 9. That will come to 41/3. So all we now need to do to find the equation of the quadratic is to put it in that structure we mentioned before. The new quadratic will be x squared minus the sum of our new roots, which was minus 26/3. So it's minus 26/3 lots of x. And then we're going to add on the product of our new roots, which is 41/3. And that's going to be equal to 0. There's only one problem. First of all, we could tidy up that minus minus that's happening in front of the x to make that a plus, but also we want to find a quadratic with integer coefficients, which of course we currently don't have. However, luckily that's very easy to fix, because as we already mentioned, there are multiple different quadratics that all have the same roots as each other, but the good news is they're all just going to be multiples of each other. So therefore all we have to do to convert this into a quadratic with integer coefficients but still has the same roots is multiply this by a number that eliminates the fractions. In this case, we just have to multiply everything by 3, therefore meaning the final answer is 3x squared plus 26x plus 41 equals 0. And there you go. Before we move on, it is worth acknowledging that in situations where we're finding a new equation for roots that are a linear transformation of the roots we had before, there is an alternative way of finding that out. But that is something we'll cover in a different video. But something else I would like to cover today is we also have to deal with situations where the roots haven't just been transformed linearly, they are combined in more bizarre ways. But the good news is, in reality, these questions are no more difficult than the one we just did, they just look a bit more weird at first glance. So again, we've been given a quadratic which supposedly has these unknown roots of alpha and beta, and we could go ahead and start by finding expressions for alpha plus beta and alpha beta, because this is a roots of polynomials question and therefore it's probably helpful to know that information. So the sum of the roots is just going to be minus the b coefficient divided by the a coefficient, and then the product of the roots is going to be the c coefficient divided by the a coefficient. But we want the new quadratic that has roots 5 alpha plus 4 over beta and 5 beta plus 4 over alpha. Looks scary, but we still just need to work on finding the sum of the roots for these new roots and the product of these new roots as well. So let's just go ahead and do that. So the sum of the roots is 5 alpha plus 4 over beta plus 5 beta plus 4 over alpha. And the nice neat thing is, due to the nice symmetry of the way these roots are formed, when we do this sum, then we are just going to end up with 5 lots of alpha plus beta, factorising the 5 out of those two terms, and we're going to end up with 4 over alpha plus 4 over beta, which is something you can then just simplify by trying to combine the fractions. And if you make a common denominator and then add the fractions together that way, you'll end up realizing the fractions can be rewritten in this particular way. So therefore that's good, because this means we've expressed the sum of the roots in terms of these things that we've already found before, alpha plus beta and alpha beta. So therefore we are going to need to do 5 times by minus 1/3 plus 4 lots of minus 1/3 divided by 10/3. That will come to minus 31 over 15. And then working out the product of these two new roots as well will get us what you can see me writing out on the screen right now. Of course, we've then just got to multiply out the brackets, which will get us a 25 alpha beta. 5 alpha times by 4 over alpha will just get us a positive 20. The 4 over beta times by 5 beta will also get us a positive 20. Luckily, alphas and betas cancel out for both those terms. And then lastly, we get a 16 over alpha beta. So actually, that's very easy to calculate. So it's just going to be 25 lots of 10/3 plus 40 plus 16 over 10/3. That will come to the fairly large number of 1922 over 15, but therefore if we now need to find the equation of the quadratic that has these new roots, it's just going to be x squared minus the sum of the roots, which we already found was minus 31 over 15, and that's going to be how many lots of x we have, and then we've got 1922 over 15 will be the term we have on the end. Again, we can do some simplifying by making that minus minus a plus, and although the question doesn't ask us to eliminate the fractions in this particular case, I'm going to anyway, just to make it look nicer. So multiplying everything through by 15 will get us 15x squared plus 31x plus 1922 equals 0. Don't forget the equals 0, because otherwise it's not an equation, so that's important to note as well. Okay, as mentioned, there is an alternative way of doing these questions if the roots have just been transformed in a linear way. That means just multiplying the roots, or the old roots I should say, by a number and then adding or taking away a number from them. But that is something we'll cover in a future video, so look out for that. But hopefully you found today's video useful, and I'll see you in a future one. Goodbye!